The nature of energy. So thermochemistry, we're looking at the relationship between chemistry and energy. So we have to define some terms here. What is energy? Scientifically, energy is the capacity to do work. It doesn't mean that work is actually being done, but capable of doing work. Well, then we have to ask, what is work? Work is a force acting over a distance. So when I pushed this cart over here, I was doing work. Heat is the flow of energy that's caused by a difference in temperature. So, you pour yourself a glass of soda, and it's room temperature and like that, and you put some ice in it. Heat is the flow of energy. The heat goes from the warm soda to the cold ice. The ice warms up, the soda cools down. So energy can be exchanged between objects through contact. Like you put ice in a warm drink, and through that contact, heat is exchanged, energy is exchanged. You hold a hot cup of coffee, energy gets transferred in the form of heat from the hot coffee cup to your hand, right? So it's helpful to think of energy as a quantity that can be possessed, kind of like money, right? So an object has a certain amount of energy. Looking at billiard balls. This ball is rolling. It's rolling, it has kinetic energy due to its motion. Heat and work are not energy, but they are ways that objects can transfer energy, can exchange energy. So when this ball collides with the purple ball, there is an exchange of energy. Here, it's doing work. So this ball pushes that ball, work is done, energy is transferred, and now this ball has the kinetic energy, and the white ball is just kind of sitting there. So energy can move out of an object, as we see here with the white ball. Energy is moving out through work. Energy can move in through work or through heat. Any questions?
I'm just wondering, when the billiard balls make contact with one another, is there technically some heat being transferred as well, but it's very minimal that you can't detect it? Okay.
Yeah, nothing real life sized is going to be a perfectly elastic collision. And so when those billiard balls collide, there's the transfer of kinetic energy, but every time we transfer energy, we lose some to heat. Yeah. Different types of energy. So kinetic energy is the energy of motion. Thermal energy is the energy associated with temperature. Thermal energy is really just a special kind of kinetic energy, because we just talked about gases, right? And the temperature is related to the average kinetic energy of the gas. And so thermal energy is how fast are the individual particles moving within the substance. Potential energy can come from the composition of the object or its position. So, we have what can I drop? I'm going to drop the meter stick. Hopefully it won't break. So I hold the meter stick out like this, and if I drop it, what's going to happen? It's going to fall. Does it have much kinetic energy right now? It's not moving. But when I drop it, it moves. It starts to move quickly, and it's got kinetic energy, right? So the potential energy it had when it was held up here gets transferred into kinetic energy, and then what happens to that energy when you hit the floor? It gets dissipated as heat. And it's so little heat that it doesn't feel warm, definitely not burning your fingers. So potential energy, we often think of, things elevated that can fall. Well, chemical energy is a type of potential energy, but here it has to do with the composition of the substance and not its position. We're looking here at the relative positions of the teeny tiny particles inside, right? The nuclei and the electrons, their relative positions. Some compounds are like compressed springs. A compressed spring has potential energy because you release it and it goes boing and it'll push something away. Some compounds are like compressed springs. If given the chance, they will release a bunch of energy. Think TNT or dynamite or gasoline, right? Compressed energy, basically. So the energy gets released in a chemical reaction. So this is a flow chart for those of you that find them useful. So energy is the capacity to do work. We've got kinetic energy due to motion. We have potential energy. This is due to position or composition. Under kinetic energy, the energy we are most interested in chemistry is thermal energy, which is related to the temperature. The potential energy we're interested in is chemical energy, and it's the positions of electrons and nuclei rather than the position of an object above the surface of the Earth. So we've learned about the law of conservation of mass. This is the law of conservation of energy, which says that energy can be neither created nor destroyed. You can transfer energy from one thing to another. It can go from one form to another form, but the energy is still there. So here, the ball being dropped, this has gravitational potential energy. When it's released, that potential energy gets turned into kinetic energy. As the ball falls, it's moving faster and faster. When you compress a spring, push down on the spring, you're giving it mechanical potential energy, and when you release that, then it transfers into kinetic energy, energy of motion as it springs upward. So we can look at the transfer of energy between two things. And, we have to specify, well, what things are we looking at? So in general, we talk about the system and the surroundings. The system is whatever material or process or object we're studying. You can define that however is convenient. It's what we're looking at. So if we're talking about hand warmers, our system might be the iron in the hand warmer. And then the surroundings is the rest of the universe. So the system is this piece of the universe that we're looking at, and the surroundings is everything else. Now, a lot of times we don't have to consider the entire universe. We can just look at the local surroundings, right? So with your hand warmer example, you're going to see an effect on your hand, on the air in the glove, and maybe on the air outside the glove. You're not going to see any effect of that hand warmer in Nebraska, right? It's just too far away. So a lot of times, we don't have to consider the whole universe, but it's anything that's around what we're looking at. So conservation of energy means that whatever is lost by the system is gained by the surroundings. It might not be the same form, but it's the same amount of energy. So if we think about measuring the energy of the system and the surroundings as being like a gas gauge, right? So here, the system's gauge is half full and the surrounding gauge is a quarter full. And then something happens and energy is transferred. This one lost a quarter tank of energy. This one gained a quarter tank of energy. It's like money. Energy is a lot like money. When a monetary transaction occurs, money transfers from the buyer to the seller. Does any money disappear? No. Now, you might have to pay some to the government for sales tax, but the money's still there, right? It's just not yours anymore. The total amount of energy is constant. Of course, you can't quite say that about money because they keep making more, but that's beside the point. So energy can be measured, so of course we have to have units of energy. So if we think about an object that's moving and has a mass m and a velocity v, the kinetic energy would be 1/2 the mass times the velocity squared. So if we use the SI units, kilogram for mass and meters per second for the velocity, we get the velocity squared is meters squared per second squared. So energy is a kilogram meter squared per second squared. This is the one I had trouble remembering. One of the ones. And so that has a special name. It's called a joule. And it's pronounced just like a jewel in a crown. Joule. It's Joule. Abbreviation is capital J. This is a small unit. If you think about a 10-watt light bulb, that's going to use 36,000 joules in an hour. That sounds like a lot, but it's because joule is a very small unit. So we'll often use kilojoules. We can stick any of those metric prefixes in front of the unit to change its size. So a kilojoule is 1,000 joules. There are other units of energy. The other one we run into in chemistry a lot is called the calorie. So the original definition of this was the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And they picked that because that was something that they could reproduce. You know, calories came about long before we had fancy computers and things to measure energy, right? So that's the calorie. And a calorie, abbreviated CAL, is equal to 4.184 joules. And this is an exact conversion. This was the original definition. It's been slightly redefined to be exactly 4.184 joules. Now, the calories we talk about in everyday life are nutritional calories. And those calories have a capital C because they're bigger than the calories with a lowercase c. And yes, this gets a little confusing sometimes. So we have big C calories and little c calories. So the big C calories are actually 1,000 of the little calories, or a kilocalorie. So I have been known to try to trick you on an exam with big C calories and little c calories. It's not a typo if there's a big C. Big C and little c are different, okay? You're definitely going to run into it in homework and probably a worksheet or something. PG&E uses a different unit, a kilowatt hour. That's a much larger unit, and that's what they use to measure your electricity. So here we have the relationship between calories and joules, nutritional calories. So that's 1,000 regular calories, or 4,184 joules. And there's the relationship between kilowatt hours and joules, just in case you need it for a problem. There will be no kilowatt hours on an exam. And this is just to give you an idea of the size of these things. You think about a human being running a mile, right? In joules, 4.2 times 10 to the 5th joules. Kilowatt hours, 0.12. So the size difference is considerable.